Today's webinar is looking at how to demonstrate and show advanced hearing aid features using relay measurement and visible speech mapping. I must first of all give a slight disclaimer that this will seem a little bit more commercial than webinars that have previously been presented by the Academy in the past, and that's mainly because we're looking at hearing aid features and some of functionality that different hearing aids can provide. So before we begin, let me just introduce myself. My name is Mistry. I'm an audiologist, educated in the UK, and I've worked in the UK on the public sector, which is the NHS. That's our public health system here in the UK. I began working for Interacoustics UK in 2011. I initially started working for the Interacoustics sales team as a trainer and some technical support, new customers buying and working with our products in different settings. And then in 2013, I moved to Interacoustics global headquarters, which are based in Denmark. And I've been working in this role ever since as that position. And in this role, I'm primarily focused on clinical support and clinical input towards product development in the fitting product area. So we're looking at relay measurement, RECD, some audiometry aspects, and video otoscope. My role predominantly focuses on talking to key opinion leaders, looking at trends in our industry, within hearing aids, within hearing aid fitting, and implementing that towards our products. So then we have a nice relevant product in the market, well used by our customers and enjoyed by our customers. Here on this screen are my contact details as well. I have contact details on the last slide too. Should anybody have any questions that aren't asked or answered during this session, then we can quite easily communicate after this talk. We can have a chat there. That's great. This presentation, it should typically take around about 30, maybe 40 minutes. We're going to look at how relay measurement and visible speech mapping can help you to demonstrate and verify advanced hearing aid features. Now, this is something that many promote and are differentiating factors of why the patient chooses a certain hearing aid or not, but also when you're asked about them, it's nice to be able to explain or show what that is and why they should go to a better hearing aid compared to another one. And typically, advanced hearing aid features are designed to keep what we want, and in the form of human communication, that's speech or a target speaker, and remove or reduce what we don't want. And we call this noise, but actually it could also be speech, but it's the non-target speaker. It could also be a baby crying, or maybe traffic noise, or even just sounds of like a fan nature or something like that, interrupting or hindering what you want to hear as a target. So we're going to focus on the following features within this presentation. First of all, frequency compression and frequency transposition. So these are typically frequency lowering features, and I'll explain them as well before we go into showing how they work. I'll then go on to noise reduction and explain how noise reduction works ahead of how we verify it or demonstrate it. Finally, microphone directionality. Once again, all of these features and anything that's seen as an advanced feature for a hearing aid is typically looking to improve the signal to noise ratio, so make the signal louder than the noise. Then that gives the best listening environment for the wearer. This presentation is following on from a presentation that my colleague Lee Martin gave a couple of months ago, looking at moving beyond audiometry. And in that presentation, he highlighted specific audiometry tests, such as the 10 test here, Quicksin, and the acceptable noise level, which through performing would allow you to identify where these type of tests or features may be required from the user or would be suitable for the user. I recommend as a refresher or as a recap, you go back to our website and you have a look at that. It's a nice thing to have a look at to see how, first of all, where they're identified and then finally how they're applied. So, before we begin, let's ask why. Why should we measure these advanced hearing aid features? First of all, we can use it to confirm a feature's performance or the way that it's working. So yes, maybe we have demonstration in the software or in the fitting tool to explain that this is how this is working or this is how this should work, but it's nice to confirm that it is also working on the patient's ear when we're running it. So it's a nice way to see and check that it is doing what we're promising. We can also use it to compare hearing aids. So yes, even though multiple hearing aids have noise reduction features or frequency lowering features, their application or the way that they do what they do may not be the same in every manner. It can vary. They can have different methods or philosophies in the way that they want to carry that out. So it's a nice thing that we're able to show and compare different hearing aids, or it may even be that you're comparing different settings of these features within the same hearing aid. So maybe a softer or a louder application. And it's allowing us to see that, and that's what we really want to do here. We can use it to set expectations. So let's say that we have a patient who is a helicopter pilot. Giving a patient like this a feature which is titled noise reduction, automatically he may have incredibly high expectations that this is going to make his life and working life much easier, and that it will be absolutely silent while he's flying his helicopter. However, that's not always the case, and the way that this is working doesn't typically identify that that's how it's going to be done. So by explaining and showing this, it helps him to understand how his hearing aid should be performing and help him understand what limitations that's got so that he uses this better and doesn't come back to return his device or stop using it at all. We can also promote better technology through showing how these features are working. So if we can show more modern or newer features or newer forms of this technology, we can encourage use of that over older forms or not using those technology forms at all. So it's a nice way to demonstrate so that then we can actually apply it a bit better. And that leads me quite nicely into the final point that I make here. So we can use it to demonstrate how a feature works. This also helps people to understand the limitations and how to get the best out of their hearing aid in different scenarios. So let's say if they're at a restaurant, where to sit, where to position themselves, and how to work with their device when talking to people. So let's first look at frequency lowering technologies, and I've singled out frequency compression and frequency transposition as this is probably the widest or the biggest used ones in the market. So let's explain how this feature works. Typically we have normal hearing, and let's just imagine that this is our basilar membrane laid out with low frequencies at 1 all the way up to our high frequencies at 7. And the connecting, let's say that the connecting inner hair cells at 6 and 7 are dead. So we could predominantly say that that's a cochlear dead region, and the patient is really struggling to hear sounds coming in this area. And this is where frequency compression and transposition start to help. Let's have a look at frequency compression first. Frequency compression, and emphasis on the word compression here, is compressing or squeezing down the sound that would typically appear here for the patient into this area of audibility at 5. So by squashing this down, we're sharing the nerve cells and areas of the basilar membrane and inner hair cells, particularly be for frequencies at this region, but they're also taking in sounds from this area too. So this is good because we're moving this energy so that it becomes audible, and we're also maintaining the natural sound that we've got in these lower frequencies here. Let's look at frequency transposition now. So frequency transposition is a little bit different. This maintains the natural spectral form of what we see here. It's the same as what we see on the top, but they apply what we would kind of see as more of a copy and paste method. So they're copying the sounds from this inaudible area here and pasting them exactly with the same spectral form on top of these areas of audibility here. This is using much more of this person's dynamic range and functional hearing, but we're also maintaining some of the natural signal characteristics here rather than squashing them together. Finally, more modern solutions that we're seeing today are actually maintaining the stimulation of the sound in this area of inaudibility or area of cell death. Now you may look at that and think, well, why would you do that? If they can't hear there anyway, then why amplify in this area that they're probably getting no benefit from? And actually there is benefit to this, and it's typically for the higher harmonics that this causes. So resonations at higher areas of the frequency bandwidth in their audiogram, which contribute to naturalness of sound. By having these harmonics or having these multiplications of this sound, it allows them to get a more natural sound out of what they're hearing. This is just a summary of how this feature is working. But how do we verify it? So first of all, I've got this process here, which has come from the DSLIO, which is from University of Western Ontario, and that's where I'm explaining this process from. You can access this as well quite easily from their website, which is up here. Basically, what they say, first of all, fit the hearing aid with the feature off to firstly determine that we're getting a good match to target, and then we're going to find this MAOF value. And this is a very special area. It stands for maximum audible output frequency. And it's typically seen to be a target for how we can then amplify and verify this type of feature. We'll look at that and I'll explain it a little bit further on the next slide. Once we've identified the MAOF, we can then move on to measure the performance of the hearing aid with the frequency lowering feature off. But we're using a special signal this time, and this signal specifically is focusing energy into the area that they aren't hearing, because we want to be able to show that we're making that audible to them. Again, these signals are special, and they were also developed in the development of this paper up here to give that energy. So I recommend you have a look at this here in order to acquire special signals if they're not already in your system, as they are in our products currently. So we measure the special signal with the feature off to see the output. We then turn the feature on and measure the same thing again. So ideally here, we're starting to see that we're making that sound which was previously inaudible audible through the use of this feature. And I'll explain this as well in a moment. Once we've got this, we can then move on to comparing these measurements and altering the feature settings to hit this target or stimulate this MAOF that we've just identified. For this measurement, the patient is facing forward towards the speaker with this special SS stimuli coming from the front. So let me just walk through those steps now with some examples. So first of all, we fit our hearing aid. I've used a broadband signal here, ISTS, in this scenario, and I've given it a fairly good match to the target that was relevant for my client here, given the limitations of the device, specifically the bandwidth in relation to the patient's audiogram, which is this shaded area here, and also the coupling, so how deep the mold was in relation to this low frequency gain that we've got here. But otherwise, it's a fairly good match to target. We can see as well that in these higher frequencies, the audiogram, or the patient's threshold, is not stimulated above 4 kilohertz. And that's because this is that area of dead region. Now, our MAOF is this region here, and it's typically, or it's identified and defined to be, the point at which the long-term average speech spectrum, this dark blue line, crosses the patient's threshold, up to the point at which the peaks in the signal, which is this area here, cross the patient's threshold as well. So let's just enlarge that. And what we can see is at this point here, the long-term average speech spectrum is crossing the patient's threshold here, up to the peaks in this area. So that area is determined as our MAOF. And that, in this scenario, is shown at 3.8 kilohertz, which is ideally, it could even be termed as an edge frequency, the last hearing area before the dead region. This is the area that we want to move this sound into to then give stimulation. The first measurement that we do with this feature or with this special signal, again, the feature is off and the signal is applied. Notice the signal shape here. It's a very high frequency focused. It's like a hiss, like sss, and we're playing this in this region. And what you can see with this feature off is the hearing aid is not able to give amplification of this signal above the patient's threshold and into their dynamic range. So actually, this is really symbolizing that, well, a feature like this is required so that they can make sounds like this audible. We can then move on to turning the feature on and applying the stimulus again. And what we can see instantly is this signal, which we played here before, is being moved across and lower into lower frequency area to give stimulation in that area that we identified. And this is what we want to see, really. Basically, the signal is changing its shape. So the input is the same, but the hearing aid is processing to play a slightly lower frequency output, which is actually falling in the patient's audible range, giving them detection and ability to hear this type of sound. We then go ahead and optimize this setting. So within different hearing aid manufacturers' software, they have settings to adjust the frequency that you're moving it down to. So as we identified there, it's good to move it to 3.8 kilohertz, but there's typically settings to move it to that or lower. And you can also adjust as to whether you want to increase or decrease the strength of this sound. So you can make this louder or softer based on how the patient feels that is helping them or not helping them. It does take a little bit of getting used to, mind, because it is kind of changing the signal that they would have typically been used to had their hearing been normal. It would seem a bit strange for them initially, but it's giving them a wider range of frequency sensitivity than what they had before, or at least detection of that. It's here that you then optimize the setting. So based on the patient's feedback, if they like it or they don't like the sound, for their loved ones who may have joined them for their appointment, based on their loved one's feedback or how their voice is sounding. But you can also choose to run another stimulus, which is very similar to this one, which is the SH stimuli. Now, this is very similar to the SS, and it was developed in the same way by the same people, but it's a little bit lower frequency. It will typically fall in about just here, and it's good to allow or to identify that the patient is able to differentiate between these two signals. You could also apply some very basic speech tests within the clinic, such as the pleural test, where you apply wording from behind the patient or from an area where they can't see your lips to see if they're able to identify whether the word that's mentioned is a plural or not. As example, cat or cats, that very soft emphasis of the S is basically the application of this feature. Finally, it's also a benefit to be able to run this special SS signal at a lower intensity. In all of these examples, we've been running them at 65 dB, which is average speech, but it's also nice to play this at a lower intensity to just check that the softer stimulations of this are also audible or not irritating for them. All of these features that I'm going to show in this presentation today are visible through the use of visible speech mapping, and visible speech mapping updates very quickly to allow us to see changes in the hearing aid settings in real time. So I've made a very short video for you where we're playing this SS stimuli constantly, but changing the settings on the hearing aid so that we can see the differences in the output. So let me just press play now, and I can talk you through what we're seeing. So first of all, we start up, and here we have the amplified SS signal, and here's his signal shape without any amplification, and the feature is off. So automatically there was no audibility there. Now we've turned it on, and we can see the images that we had before, and we can see very quickly that we're giving stimulation now in the patient's dynamic range. I've now adjusted the setting to give a lower frequency stimulation, so you saw that curve move to the left. And then I'll move it again to an even lower frequency. So again, even lower down the audiogram frequency-wise, we're stimulating much lower. At the end, I'll turn it back to the original setting. And just for example's sake, I'll turn on the additional amplification of those frequencies that I mentioned at the start, where we maintain the original amplification for those higher harmonics. I'll just play that again for you. So first of all, without the feature on, we then move to turning the feature on and showing that we're then stimulating into the patient's dynamic range. I'll then adjust it to make it lower. So you can see it coming down a little bit now. And then I'll make it even lower. So I think this is the maximum setting that I could set it to for this hearing aid that I was working with. Now, you might ask, why does this shaded area update much faster than the target line? And that's because this is based on the long-term average speech spectrum. So it's averaging much slower than the shaded area, which is a live representation. It's updating very quickly. So the final screen that we see here is the setting applied with the harmonics turned on, so with the existing stimulation enabled. Let's move over now into the next feature, which is noise reduction. Now, noise reduction, let's have a look at first of all how the hearing aid is working without noise reduction applied. So we have speech at a constant level, and when we begin to measure the output of this, we get a nice response which shows very cleanly this is what is happening as the signal is coming in. Should we introduce a noise source into this environment, that will automatically make the total environment louder. So we then record something which is slightly higher, but we've got a much dirtier signal. Well, I say dirtier because we've got product in there that we don't want, which is the fan noise, in addition to the speech. So the signal to noise ratio in this curve, even though it's louder, is containing both speech and noise, which is not what we want to do if we want to allow the patient to hear the speech better than the noise. So now when we turn this feature on and we measure again, what we'll see is that the noise is then reduced, and we can then measure a lower signal, but actually we've cleaned the noise out of that. So even though the output is reduced, it is a much cleaner signal with better signal content. And this is ideal, really, because we are then optimizing that condition and that listening environment for the patient. So how do we demonstrate this? So first of all, we want to make sure that the hearing aid is fitted correctly. This is to the patient's preference and ideally to a target algorithm that's independently verified. We'll then go on to playing a pink noise stimulus or a static noise stimulus, something that's playing the same frequency content over and over. And we want to turn off our noise reduction feature at the beginning. So we want to show what is the effect without the feature on, or the before in this scenario. We then do the same again, but we turn on our feature, and that gives us our after. And then we can finally compare these measurements and adjust the feature settings based on the patient's preferences. For this scenario, the patient is sitting forward to the speaker with pink noise playing from the front. You could also do this as well with speech coming from the front and noise coming from the back or the side, but that might also creep into the next feature, but we'll talk about that in a moment. But ideally, we're playing noise from the front with the feature off, and then we play noise from the front with the feature on. So let's have a quick look at that now, or at least an example of the measurement. So here we can see that with the feature off, we get a louder curve, and then when we enable the feature, the measurement that we are acquiring is a bit lower, and this is the noise reduction functionality coming into work and into play. It can take a little bit of time to activate the noise reduction feature because the hearing aid needs to identify or even look at the incoming signal. So they're very clever in identifying what is noise and what is speech. You can do this in a few different ways, but specifically it's looking at the spectral and the tempo, the speed analysis of the incoming signal. Speech is very specialized in that way, where it has a certain spectral form and speed and how fast it's changing, compared to a constantly spinning fan, which could be seen as static. It would still play all frequencies, but at a more controlled rate. So the hearing aid could give amplification focus on the more dynamic signal, in this case speech, and give less of an amplification focus for the static noise, which is why you may see like this. Some of the more traditional methods of this form would just basically cut amplification in the lower frequencies. So they would identify noise as being predominantly more lower frequency focused and keep the higher frequencies. Again, it's a different application, and measuring in this way allows you to identify what the feature is actually doing compared to how it's written or shown in your fitting software. Again, visible speech mapping is a really nice way to demonstrate how this is working, and I've made a video. As I mentioned before, it is a bit slow to show this feature coming into play, so I've sped it up a little bit just to emphasize it. So I'll play this twice. I'll first explain. So here we have our pink noise playing, and the feature is off. So notice there that the response is pretty much stuck. It stays in the same position. Nothing else is reducing or changing. The second measurement comes in, and this is with the feature on. And what you see there is actually, after a few seconds, it recognizes that there is noise there, so the output is then reduced. I'll just play that again. Oh, and sorry, before I play that, both signals, which you can see over here, the unamplified, this is the external microphone, shows that the input to the hearing aid is the same in both scenarios. The difference is only what we see at the probe microphone, or at basically the sound coming into the eardrum. Just play that again. First of all, without the feature on, and then the second play is with the feature on, and it starts off a little bit, and then it starts to reduce, showing that the feature is starting to work. So let's now move on to the last feature that I'm discussing in this presentation, and this is specifically microphone directionality. So here we have my patient head, and like we hear normally, we have equal sensitivity from all directions. So here we have, when we discuss that from a microphone polarity perspective, this is omnidirectional. So all sounds from all directions are equally sensitive and amplified. This is great when we're listening to speech, or when there's mainly signal around us, so there's mainly speech that we want to hear. It's also good when you're facing forward to face the speaker that you're listening to. However, should we introduce a noise signal, in this case a static fan, then actually we're getting equal input from this fan noise and the speech. So we're starting to get a slightly dirtier signal. I say dirtier, or I mean a lower signal to noise ratio. And with microphones which are directional, what they can do is they can focus their sensitivity more to the front or facing the speaker. So what we've got here, let's play that back again, the microphone is now giving emphasis or priority signals to signals coming from the front, and reducing or ignoring the signals that are coming in from the back. I say ignoring, it's not a complete cut, it's more of a reduction in sensitivity. Now this is great, especially in this scenario where the patient is facing the speaker and the noise is to the back. But let's say that a speaker then, or another person comes in from the side. Let's say that this is a dinner party where you're sitting at a table. In this scenario, this person sitting over here is less audible than the person sitting at the front. And what modern hearing aids do today, they'll have a couple, if not several, different filters that are constantly scanning in this environment, shaping their polarity towards different speakers. So in this scenario, even though the patient is still facing forward, the polarity or the filter and the sensitivity of the microphone is able to adjust to give focus to the person, to the people's voices, again through spectral analysis, and give less of a priority to the noise that's coming in from the back. This is really good in a group environment because it helps us to pick out what we want to hear and ignore the noise aspect around it. So how do we demonstrate this? And again, I've got another process. So first of all, make sure that your hearing aid is fitted correctly. We can then move towards playing a ISTS signal or a speech signal from the front and a noise signal from the back. And again, specifically static noise, similar to pink noise or white noise, or even a radio tuned out to give like a shh or a shushing noise, like running water almost. Again, we want to get to before, so we would turn the feature off so we understand what the hearing aid is doing without that feature enabled. And then we run an after. So the patient is still in the same position with the same signal, speech from the front and noise from the back, but we have the feature on this time. Then finally, we can compare these measurements and adjust the features in the settings. So here we have our patient sitting forward to the noise, sitting forward to the REM speaker with ISTS coming from the front. This is typically the best speech-based signal that we use for fitting hearing aids. And then they have static noise coming at them from 180 degrees, so from behind them. Here's an example of how this is working. So what we can see first of all is with the feature off, we have a louder signal. But remember, the signal-to-noise ratio content is lower here because we're containing both the noise and the signal together. And then when the feature is enabled, we see a lower curve coming out, but it's much cleaner. We're getting more of the speaker focus. It can be a little bit difficult to play this static noise from the back of a client or the patient that you have. And what I recommend when you're doing this is to play a radio which is tuned out to play like a white noise or even Gaussian noise from the back, or even use a small Bluetooth speaker to play pink noise through. Now, I found a pink noise track on YouTube, and it was quite easy to play that through this small speaker from the back of the patient. So it was easy to recreate this environment. It's really crucial that you have the same conditions for measurement 2 here and measurement 3 with the feature on and off to allow you to compare the two together. Good. As before, I have a video again. Again, it's sped up because these features take a little bit of time to recognize the incoming signal to then decide how it should process. So let's just play that now. First of all, we see the signal coming in, and then we start to see the second measurement, which we've applied the feature to, and then we see a reduction in the input, as we can see here. I'll just play that again once more for you. So first of all, with the feature off, and then in the second measurement, we apply the setting on, and then we can go ahead and show this lower input from the hearing aid, or lower output from the hearing aid, because this feature is applied. Please also notice that one of the nice things about visible speech mapping here is you can see the unamplified incoming signal for both measurements here, and notice that both are on top of them. This isn't a signal manipulation, it's a processing feature of the hearing aid for all three conditions, which show that they're giving a different output based on whether the feature is on or off. So I'll just play that once more for you, just with emphasis over here. I may have gone a bit fast there, but this has brought us towards the end of this presentation, and I just want to summarize as to what the aims of the webinar were. First of all, I've given some understanding of how to verify frequency-lowering hearing aids using REM and visible speech mapping. I've also given an understanding of how to use REM and visible speech mapping to demonstrate directional microphones and directional microphone features or directionality features of hearing aids. And then finally, I've given an understanding of how to use REM and visible speech mapping to demonstrate noise reduction algorithm. Thank you very much for attending. I'd now like to invite any questions. Please write your questions in the comments bar on the left-hand side, and we'll go through these with you.
We've got a question coming through, Dennis, which I'll just moderate these, if that's all right.
Yeah, that's perfect.
I'll just read them through for you, and then you can have a think whilst we're reading them out. So first question's come through from Richard Mitchell. So his question is, are the side-by-side VSPM views set up as standard or by the user?
So the side-by-side view that I have there, I can go back to that in my presentation as well, actually. Let me just pull that up. This view here is by default, actually. So we've got on the left-hand side, unaided, and this is showing what's coming in at the reference microphone of the headset. And then we have aided, which is showing what's being measured by the probe microphone of the headset. So in a way, you could look at this as a signal that's coming in and then what we're measuring out from the hearing aid, so before and after. So yeah, this is a standard view. You can choose to configure it so that then you can view left and then right, but it's a specific feature of the visible speech mapping window.
We have potentially a question coming in from Lim Sherman.
Yes, that's great.
So we're just waiting for that. So Lim's now followed up with, for frequency compression, it's true we are able to see how the frequency shifts when we do frequency compression, but I don't think we can really show how much speech may be distorted. So I guess that's more of a comment, and maybe for your thoughts there in terms of what so you think.
Let's have a look back at that there actually. So one key word that's been used in this question that I think is very, very useful to discuss here is distortion. Remember, we are changing what is heard by the hearing aid user compared to the incoming signal. And by placing these sounds in this area, we are providing distortion to them. So yes, we add this here, but we're also affecting 5. And we add these in this scenario here, but we're also affecting 4 and 5. Yes, this is distortion, but ultimately we're providing audibility of these areas here that they were previously inaudible to them before. And actually, this is more of a preference. So it's completely up to the patient as to whether they feel that this is useful or distracting. And that's really key when we're fitting algorithms like this, especially on children who are unable to report it back to us, that we apply what we feel is useful and not something that's going to deteriorate or reduce their performance. It is difficult to measure in this scenario what is useful sound, because then that relies more on cognition or audibility and also higher lesions of the brain for speech understanding. But ultimately, if we improve or increase the incoming signal, if we give them a higher signal to then be able to process with, we can then allow their auditory pathway to be able to sort between that information as to how it's used. There is a lot of evidence as well to show that frequency compression, frequency lowering, frequency transposition is very beneficial to users. So I mean, as long as it's optimized properly and controlled, I say that because I know that it's very easy, and I've seen it's very easy to just turn it on for everybody, but there's no recollection or knowledge as to how much of a benefit it's giving. So think things as well like the plural test, as I mentioned before. So cats. So tell me if there's 1 and 2. So if they're able to hear in that higher frequency region, then they'll be able to identify when I say cats and cat. That's a real good application or real good test of the application of this type of feature.
So Lim is just coming back now saying, sure, I'm just thinking how I can counsel my patient when I'm showing visual speech mapping, hence thinking towards the practicality from a counselling perspective. Yeah, thank you for sharing your advice.
Good point. So let's have a look at the graph that we see. So I think when counselling for such a loss and such feature, I'd first of all start off with the limitation of their hearing, in that in these higher frequency regions, their hearing is so poor that the signal on its own is inaudible. So they're missing areas of audibility. They're missing areas of sound which allow them to identify speech. I then also bring in that in order to make the sounds here available, we have to move them down, because the hair cells and then the signal going into the auditory pathway is not good enough at bringing this through to allow them to use it. That instantly states that there's a limitation to what we have from their hearing. Moving on from that, it's nice to show, as I've shown on this second screen, the signal alone with the hearing aid optimized to their preferences cannot amplify into that area as well. Therefore, by placing this signal in this area, yes, it will be distorted. Yes, it will be different or sound strange to them, but it gives them access to something that they would otherwise not have any access to at all. And it's completely an adaptation thing. And it may even be useful to apply 2 programs to that hearing aid where we have it on and have it off, and allow them to try and adapt and use that in different environments to then see what benefits it brings.
Excellent point, as always, Dennis. And a lot, as Lim has been put into that, is counselling and individual patient preferences. So thanks very much for your questions, Lim.
I've really seen some variable inputs to this. I've had patients that I thought would really like it that don't like it, and I've had patients that I thought it wouldn't work for it all, really prefer that sound. So again, it's a lot of preference, but also it's the explanation of the limitations and what they expect from what their hearing aid will give.
I think that's the close then of questions coming in.
I think that one, just as a final point there, I think is quite useful. Counselling. I think that this is a really nice thing to be able to show, to be able to explain and counsel these type of features. I know, so I'm going to zip back. I know at the start of my presentation where I explained why we should do this, we can demonstrate. I think one of the things that's probably skipped over here through demonstration and setting expectations is the overall application of counselling here. Remember, I'm showing each feature independently. I'm turning off other features to show the effects of one. But when they're all working together in unison, they can create an overall effect which is different to what we may see there, and also an audible effect, but a visual effect. And visible speech mapping is a really nice way to make that visible to then make it more relevant when counselling. It's a nice tool to use in that. So thank you very much for coming, and my email's there on the right-hand side should you wish to contact me and ask anything further. Thank you, guys.